Okay, so now let's continue the proof of the view. Yeah, homotopy lemma. So okay. So I think last time I okay, so I think last time we showed that the last time we showed that this h hat is continuous on the Canonical subset. Okay. So now what we are trying to prove is that okay, let's start here. Okay. Yeah, so remember that last time we already proved that. So this is after the proof of the h hat is continuous. Yeah, so last time we showed that yeah, so this h hat is continuous on the connected subset. So here I will ignore connected. So yeah, and then okay, and then hence yeah, and hence okay, so hence the image, so and let's call it S. Must be contained in okay. Must be contained in some U1 where U1 is set as that's the gamma received on this U1 is it's a homomorphism. It is a homomorphism onto U. Okay. Okay. so this is what we showed last time. Okay. And then, okay, so again, applying the local inverse, we get a continuous lifting of H repeated on D that agrees with H hat. Along the set. C minus epsilon cross R minus epsilon, R plus epsilon intersect 0, 1. And therefore, by construction, must agree with H hat all okay. So applying the local inverse, we get a continuous lifting of okay. H hat along the set. Okay, so let's see why we get a continuous lifting of this H hat D. Okay, so now so why we get a continuous lifting? We get a continuous lifting. Okay, so because yes, so the continuous lifting we simply get it from the fact that this H, okay, this H restriction on D basically maps so continuous lifting. So basically this HD is from this D to so this HD is restriction on D is from the set D. So let me remind myself what D is. So so D is a set um, yeah, so D is a set. Yeah, so basically D is just this C minus epsilon comma C plus epsilon. So C plus epsilon closed interval intersect AB times the same thing here. Yeah. Yeah. Okay. So yeah, so okay. Okay, I see, I see. Yeah, so this D actually is this H restriction D is actually let me see. Why this is why, okay, why this okay. Let's see, what we want to show. I'm not sure that whether I get a continuous lifting, okay. Of H restriction D that I agree with H hat along the set. Okay. Continuous lifting. Okay. Okay, so basically we apply the local inverse, right? So because this H, so where does H of D lies in? So, okay. So this HD, okay. Yeah. Yeah, so we apply the inverse weight. Okay, so why we get the continuous lifting? Okay. We get a continuous lifting because this H, we know that this H is, wait, do we know? Okay, this H is continuous, right? Because it's part of homotopy. And then because the lifting is a homomorphism, it's not continuous. Therefore, we get a continuous map from this D to it's from D, wait. From D to where? From D to U1. Right, yeah, from D to U1. Okay, so what is the continuous lifting? Yeah. Okay, so yeah, this is a continuous lifting. And then I agree with this H hat along the set. Okay. Okay. Why I agree with H hat? Okay. So okay, so we know that this I think we showed last time, right? So this H hat of yeah. So we show that this H hat of this X is contained in this U1 last time, right? So therefore, and then H hat is a lift, right? So therefore, yeah. Wait. Oh, okay. Because this gamma is a homomorphism, right? Okay. So therefore, yeah. Okay, what do you want to show? Okay. Agree with H hat along the set. Okay. So why it agree with H hat? Because okay. So why? So okay. So let's mark it as star. Okay, the star condition. Okay. So for the star condition, why H hat be agrees? Okay. Because if you take any if you take any yeah, if you take any let's say yeah, okay, I see. So so let's say any t, right? So wait, okay. So this lies in U by definition. Okay, this lies in U. And then we know that if we apply the gamma restricted on U1 of this point, then this must lies in wait. Sorry, gamma restricted on U1 inverse. Oops, sorry. Gamma restricted on U1 inverse, yes. Inverse. Yeah, so this okay, so why this agree with H set? Okay. Inverse. Agree with H. Oh, this is a continuous lifting. Okay. Oh. What is H hat? So H hat, I know that it is from where? Okay. H hat FS is contained in U1. Oh, I see. Okay. Because this H hat S is contained in U1, and then this gamma from yeah, and then this H hat S is by definition is lifting, right? So lifting means that when we project it down to U0. It should be, yeah. So when we project it down to U0, it should agree with this H. We should on D, right? Yeah, because, yeah. It should agree with this H. Okay. So therefore, why, wait, what do you want to show? Oh, okay, because H, oh, okay. Wait, why it agree with H? Why it agree with H hat? Let me see. It agree with H. Okay. Okay, I think the reason is that, so this H hat by the covering projection, yeah, because H hat is a lifting of this H by definition. So after projection, it will equal to this H, right? And then, because the projection is simply just because this H hat of X lies in this U1, so therefore the projection is just R restricted on this U1, right? And then, wait, well, yeah, okay. And then for this, why they agree with H? Yeah. Okay. Then you take the inverse, right? Wait, what? Yeah. You take the inverse because it's a homomorphism, so therefore it's the same. Okay, therefore it's the same. Okay. All right. So let's move on. So, okay. So and therefore by construction, must agree with H hat on all of D. Okay. Let's see why construction must agree with H hat on all of D. Oh, okay, yeah. Wait. see the reason why it's by construction. By construction. So this D is what? By construction. What does the construction mean? So, construction must agree with H hat or B. With H hat on set. Okay. H D is agree H hat. Therefore, by construction. Okay. So. And H is on D. Okay, so why by construction? You know that this it has nothing to do with the D, right? Because this D is what? Okay. Okay, let's see why. Let's see why let's say why this HD is contained in let's see why. Because basically the idea is that this H of D is contained in the evenly colored set U, right? And then we take local inverse. We know that okay. We know okay, so here we get a lifting that I think it should be agree with H of X, right? Wait, no. So okay, so is it because like any connected argument? No, this H hat may not be continuous in this case. So construction. Let's see. Look at continuous lifting H, we should do that with H hat along set. Okay. These two agree. Okay. Okay. So yeah. Oh, I see. Okay. I think the thing is that you use the because yeah. yeah, so you see, yeah, so wait, no, okay, wait, oh, I see, okay, so yeah, so this set we can think of like, so remember we have the lemma saying that, yeah, I think we just proved, I think there's a lemma we proved before, right? So namely, once you, yeah, so remember for part A, we proved that if gamma is a path in X with the initial point X naught, then there is a unique lifting to a path in, yeah, X hat with, wait, no. Oh, wait. Wait. Oh, yeah. Because the lifting is unique, right? Because the lifting is unique. Okay. Yes. Yeah, so they must agree. Yeah. Yeah. They must agree, yes. Okay. 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 Yeah. So the idea is that, so remember, like, once you, so once what so here this is like, so, yeah. So if you look at the set, right? So this, yeah. So let me remind you. So if you just look at the set, like take this image, Siemens epsilon, cross. Sorry, take this domain, cross this r minus epsilon r plus epsilon, intersect 0, 1. Yeah. So you may think of like, okay, so wait, no. Wait. Okay. So, okay. Let's try this. Okay. So, okay, instead of putting C minus epsilon, I will put, okay. So let's put this. So C minus epsilon, comma C plus epsilon, okay, intersect AB. Okay. So this is a family of line, of like a path, right? So the idea is that if we just took one path, okay, so this is like, yeah, if we just took one path, so namely we fix a t, right? And then we pull out one path, so that h, what I call it, which is on D, maybe T, which is, yeah, anyway, from, yeah, just fix this T here and then let the other variable run, yeah. Maybe I use S for T. Okay, maybe I'll use S. Okay, I'll use S. Okay, so fix the S. Let T run through this interval. Okay. Yeah, so this is S. Yeah. Okay. So now the thing is that wait. Okay. So we know that wait. Okay, wait. Okay. Okay. So okay. What do you want to say? Okay, we know that this set has a lifting to where? Okay. So so this is a path, right? So for a path, we define the h hat. Okay, we define the h hat. Remember this h hat is defined to be the lifting of this h, right? So yeah. So therefore, so there's a like a h hat. Let's say okay. H hat. Wait a minute. Okay. Okay. S. Okay. Yeah. So this is the lift. Okay. Yeah. By definition, this is the lift. And then, oh, what is the initial point? The initial point is sigma epsilon, right? The initial point is sigma epsilon. Okay. So okay. So if you take the so imagine we have a like interval here, this u naught, let's say like an open set. So if you just focus on the initial point, right? So so remember that once you fix a initial point, then there's a unique lift, right? And then because this is also a lift, right? So if you fix like a yeah. So why is the lift? Yeah, this is a lift. Of course, this is a lift. Okay. Okay. Yeah. So therefore, these two lifts agree because of uniqueness. Okay. So therefore, yeah, because wait, yeah. So they must agree. Yeah, they must agree. Okay. So now let's okay. Okay. Thus, thus, we have again arrived at a contradiction. And we see that H hat must be continuous. Okay, so why we arrive at a contradiction? So okay. Okay, I think the reason is that uh, this D is wait. Continuous lifting that is equal to X hat alone. Yeah, remember this D is actually uh, it made okay. I don't think it's a yeah. So there are some neighborhoods. Wait. Yeah. Wait. Okay. Uh, because uh, what is it? Okay. Let's see why. what is the contradiction? So, so basically, we know that this CR is contained in D, right? We know that this CR is contained in D. So therefore what? Okay, so why there is a contradiction? Because